please. Okay. Yeah, hello everyone. My name is Matthias, and I'm going to talk about a new memory allocator for GPUs, specifically CUDA. So the overall goal of my research is to make GPU programming easier to use. It is quite difficult at the moment, and I'm trying to make it easier to use for experts, from people who are not experts in GPU programming, from domain experts in other domains. And I'm trying to do this by providing fast object-oriented programming for GPUs, and specifically CUDA. And as it turns out, in high-performance computing, there are many problems which can be expressed very nicely with object-oriented programming. And as it turns out, dynamic memory allocation is very useful in object-oriented programming because it gives you this flexibility of creating and deleting object at any time. So in this work, I'm going to talk about DynaSOAr, a new lock-free dynamic memory allocator for structured data based on hierarchical bitmaps. And when I say structured, this is the main difference to other memory allocators. So in this allocator, we cannot just allocate like X number of bytes or so. This allocator is only usable for C++ classes and structs. So this allocator has some knowledge about the structure of its allocations, and this allows us to do some additional optimizations here. Let me talk a little bit about some background here. So this is an n-body simulation, the data structure of an n-body simulation. And on the left-hand side, we have this structure of arrays layout, which is kind of the standard layout in C++. So we have 32,000 objects here, and we have this structure which defines those fields. Now, on the right side, we have a so-called structure of arrays layout, and this is one of the standard optimizations for GPUs. And if you read a GPU programming book, this is one of the first things you will learn about. So in this layout, we split this array into 7 separate arrays, one for every field. Now, when we write a parallel program, we probably read those values here, maybe position X value, in parallel for all objects. Now, if this is happening, then we have much better performance with the structure of arrays layout because the GPU can vector load all of those position X values. While in array of structures, we have a much less efficient strided memory layout, or a strided memory access pattern. So this optimization, structure of arrays, is the main optimization of DynaSOAr. So one thing that is really important with a structure of arrays layout is low fragmentation. So what you can see here in figure A is a very compact structure of arrays layout. And what I'm showing here is the SOA array for this position X value. So we have 12 values here. Now, if we read all of those values at the same time, then in this example we need three vector loads for reading 12 of those values. Now, because of dynamic allocation, we can easily end up with a fragmented SOA layout as it is shown here. So we can easily end up with such a layout due to unfortunate allocate and deallocate patterns. And in this case, we need 1, 2, 3, 4, 5, 6 memory transactions. Because, basically when we read, for reading the same number of bytes. Basically because if we have a vector load here, then we're also reading some garbage data here. So this is bad. This is what we want to avoid. Now, as it turns out, the layout doesn't have to be super compact as it is shown in subfigure A. It can also be a layout that is more like this one here. So in this example, we need the same number of memory transactions, even though we have this kind of empty space in here. So as long as data is stored in blocks which are at least as large as the vector length, we are good. So, and this gives us this gives our allocator some freedom in placing allocations. So it doesn't have to be super compact. This is also fine. So here are the overall requirements of our allocator. We want to allocate stuff in SOA, structure of arrays data layout. We want to have low fragmentation because high fragmentation makes the structure of array layout less efficient. And this also means that we cannot use some implementation techniques that are used by other allocators, namely scatteralloc and halloc, which are the two fastest ones available. They use hashing. So when they allocate new memory, they use a hash function to determine the address in memory where they want to place an allocation. And this is good for fast allocations because it makes it very unlikely that two threads are trying to allocate the same memory location. But it is really bad for fragmentation, so we can end up with a very fragmented heap. So without this optimization, so we cannot use this optimization or similar optimizations, or implementation techniques, should I say. And what that means is that DynaSOAr will always be slower than these other allocators when it comes to raw allocate, deallocate performance. So the time it takes until new and delete return. But we can make up for this with better memory access performance. So the raw deallocation and allocation performance is slower, but then when we're using the memory, we can be better and we can make up for this slowdown. Also, we want to make sure that we use the heap very efficiently, so we don't want to spend too much memory on internal data structures, and we don't want to use locking. And the reason for that is that locking is generally discouraged on GPUs, so when you use locking, you can easily end up with deadlocks. So here's an overview of the DynaSOAr memory allocator. And there's one main difference between DynaSOAr and other memory allocators. So in DynaSOAr is actually consists of three components: a memory allocator, an SOA data layout DSL, and a parallel do all operation. And the main difference here is that DynaSOAr does not only control the memory layout of its allocation, but it also controls the memory access patterns. So just by having an SOA layout, we don't get anything. We also have to make sure that memory is accessed in a suitable pattern, and this is what's done by this parallel do all operation. So the way we express parallelism in DynaSOAr is with this new programming model that we call SMMO, which means single method, multiple objects. And that means that we express parallelism by running the same methods on all objects of a type. And then DynaSOAr will make sure that we assign objects to threads in a good way, and that we have good memory coalescing, so we have good memory, we have good vectorized access. So this is one part of DynaSOAr. The other one is this memory allocator and an SOA data layout DSL. So because we are storing data in a different layout, in a non-standard C++ layout, we cannot use those C++ abstractions like method calls and so on. And for that reason, we developed this DSL, which is actually described in a different workshop paper. And this allows us to use object-oriented programming with a custom data layout. But what I'm going to focus in this talk is the memory allocator. If you're interested in the other parts, just talk to me later, or you can also find details about that in the paper. So this figure gives an overview of the heap layout of DynaSOAr. So the heap consists of blocks, in this case M blocks. All blocks have the same size in bytes, and what is important here is that every block can contain only objects of the same C++ class, C++ type. So this example is taken from finite element methods, and we have classes here such as Spring, Node, Pull Node, and some other classes. Now, inside of a block, we only store objects of the same type in structure of arrays layout. So for example, here we store up to 64 objects of C++ class Spring, and we have 1, 2, 3, 4, 5, 6 fields, and we store those SOA arrays in here. So this is the structure of arrays layout that I showed you before. Now here we have different objects of type node. We have a bitmap here. This bitmap is used to keep track of which object slots are in use. Because I talked about fragmentation before, so we want to make sure that we have very low fragmentation. What we want to have is lots of blocks that are completely full, like this block here. Right? According to this bitmap, this block is 100% full. So this is good. Also, this block is empty. This is also good. These two blocks, they do not contribute to fragmentation. Now, this block is like around 70% full or so. This is not so good. This block contributes to fragmentation. And why this is bad is because when we do some vector load on these SOA arrays, then we probably also read in some garbage data of those object slots which are not in use. So this is what we want to avoid. Now, every block in this system is associated with one or multiple states. So in the beginning, let me go back, every block is in a free state, which means nothing is allocated here. Now, once we allocate something, we decide on a specific type that we want to allocate in a block. For example, this block here, we only store objects of type Spring. And now this block is in an allocated state, allocated of type Spring. In addition, this block is in an active state. And active means it is active for allocations, which means there is at least one more object can be placed in here. So this block is active. This block is not active because it is 100% full. Now, when we allocate new objects to keep fragmentation low, we always want to allocate them in active blocks. So when we allocate a new object, we find a block which is active. If no such block exists, then we have to take a free block and initialize it and turn it into an active and allocated block. And once we selected a block, we basically atomically select a bit in this bitmap here and set it to 1 with an atomic operation. That is how we reserve an object slot. So now the question is, how do we find active blocks, or how do we find free blocks? Because if no active blocks exists, then we have to initialize a new free block. We do this with an index data structure. So basically, we maintain bitmaps for every one of those states here. So there's a bitmap for every one of them. For example, if we want to allocate a new object of type Spring, we can take a look at this bitmap here. And in this bitmap, active Spring, we have 1 bit for every block. And that bit is set to 1 if this block is active and of type Spring. So we can just scan this bitmap here. Now the problem is this bitmap can get pretty large. It can become multiple megabytes in size. And for that reason, internally, those bitmaps are implemented with a bitmap hierarchy. And that means that every 64 bits, or in this figure, every 4 bits are summarized by 1 bit. And then we can find bits that are set to 1 by a top-down traversal of this hierarchy. And then we only need a logarithmic number of accesses. So this is much faster. Now, what is interesting here is that the number of bitmaps or indices that we maintain, this depends on the number of types that we have in our system. So when we initialize or when we define our allocator, or when you want to use my allocator, you have to tell it what are the C++ classes or struct that can be used with this allocator. And depending on that information, the allocator will allocate memory for a bunch of bitmaps here. So the number of bitmaps depends on the number of C++ classes. Let me briefly talk about some of the challenges here. So one challenge in this allocator is consistency of data structures. Specifically, we have to make sure that the actual allocator state is consistent with those block state bitmaps, with those indices. So, for example, we might allocate some objects in this block, and eventually this block might become full. At this point, we have to set this bit here, the corresponding bit of this block, to 0, because now this block is no longer active, it is full. But these are two different operations, so we cannot update this bitmap and update this bitmap at the same time atomically. So for that reason, some other concurrent memory operations or some other concurrent allocate operations, they might still see this bit being set to 1, but then when they try to allocate something in here, they find out, oh, there's no space anymore. So our allocator has to be able to deal with such kind of operations, with such kind of problems. And the way we do this is we always allocate stuff optimistically, and if we detect a problem, then we can roll back this kind of allocation. Now, also allocation contention is a problem. So 2 threads may try to allocate this same object slot, and that is a problem. Only one of them can succeed, the other one has to retry. Also, safe memory reclamation, this is a big one. So when we delete the last object slot in this block here, we want to delete this block. But is this a safe operation? There may be some other concurrent allocate operations, and these allocate operations might already have selected this block and they're about to allocate something here. So now it is no longer safe to delete this block. So how this is solved is described in detail in the paper, but the basic technique is that we invalidate this block, which means we atomically set all bits in this bitmap to 1, and then this block appears to be 100% full to other threads. So just a brief overview of the optimization that we have in our system. We use hierarchical bitmaps for these block state indices. We use a technique called allocation request coalescing for reducing the number of concurrent memory of atomic operations. This was originally introduced by xmalloc, one of the first memory allocators. And what that means is that if 2 threads in the same warp are allocating memory, then we elect a leader thread. The leader thread allocates memory on behalf of the entire warp, and then it distributes the allocations again to the other threads. And what that means, basically we can set 2 bits to 1 with 1 memory operation. That's what it boils down to. Another one, we have a bunch of efficient bit operations such as FFS, which gives us the index of the first bit that is set to 1. This is an operation we use a lot, and it compiles to very efficient PTX codes. Because of that, interestingly, this operation always selects the first bit that is set to 1. So if we have 2 allocating threads, they might, for example, in this top-down traversal, always select the first bit that is set to 1. So this leads to the effect, the effect of this is that we have the case that many threads may try to allocate stuff in the same block. In order to avoid this, we use this optimization, bitmap rotation. So before using FFS, we rotate the bitmap by a kind of random degree, random number, and that makes it less likely that 2 threads are selecting the same bit. Okay, some benchmarks. We benchmarked our allocator with 8 different SMMO applications, and they're from different domains. What you can see here is the red one is DynaSOAr, our memory allocator, and Halloc and malloc-mc are our main competitors. And what you can see here is that in all applications, we are faster than those 2 allocators. Sometimes by a lot, sometimes just a little bit faster. And the main reason why we're faster is because we're using this SOA data layout, and the other allocators, Halloc and malloc-mc, don't. Speaking about fragmentation, this example is an efficient shark simulation. What you can see here is the red dots, they're shark objects, they're eating the fish. And here you can see the number of iterations here, and what you see on the y-axis is the number of objects. And what you can see here is that the red line, the number of fish objects is decreasing, but at the same time, the total memory usage is not decreasing. And the reason for that is that at this point, we have lots of fish objects still hanging around. So there are lots of blocks which are like 50% full or so, but we cannot delete that block yet. We can only delete a block when the block is 100% empty. So eventually, fragmentation will go down to around 20% or so. So fragmentation is that gray area here. We developed an optimization for this, a memory defragmentation system, which can solve this problem. If you're interested in this, we described this in another paper that we published at ISMM this year. As a summary, what we found out is that it is really important not just to optimize for raw allocation and deallocation performance, but also for efficient access of allocated memory. This is the main optimization here. So we have this structure for arrays layout. Because GPUs and SIMD architectures, they require special optimizations for better vectorized access. And one thing that is crucial here is low fragmentation. Because if we have high fragmentation, then this structure for arrays layout becomes less efficient, and then this optimization no longer pays off. Also, if you're worried about these atomic operations that we're using pretty much everywhere here, these become much faster with recent GPU architectures. So this allows us to implement our memory allocator in this way. Here, this brings me to the end of my presentation, and I'm happy to answer any questions.
Okay, any questions? Oh, yes.
Thanks, that looks like very interesting work. I guess I had two related questions. One was the reduction of atomic operations by doing things on a per warp basis. Mm-hmm. Did you consider extending that to the whole thread block, having the master of a thread block allocate on behalf of the block? And the second thing is when you do things that are warp sensitive or thread block sensitive, you've got to be careful about non-uniform control flow. Is that an issue?
Oh, so your first question was if we can extend this to an entire thread block in CUDA?
That's right.
Yeah, I think so. I don't see why that could not be done. The reason why we do it on a per warp basis is because I think those SIMD lane shuffling operations are very efficient. But I guess if we use shared memory, we could also do that for the entire block.
Right, yeah, you'd have to just say if my ID is 0, then do the allocation and communicate the result in shared memory, I suppose. So, because you're in the warp, you don't need shared memory, you can communicate using private variables.
So we use we use CUDA warp shuffling to shuffle stuff to another lane.
And do you need to be careful about non-uniform control flow there? Like, what happens if you do a warp shuffle in a bit of code that's thread ID sensitive, for example? So,
yeah, I think non-uniform control flow is not really a problem here. So it could be. So one thing that can happen is that two threads in the same warp are trying to allocate memory, but they're allocating memory of a different type, for example. One thread is trying to allocate memory for class C++ class fish, another one for C++ class shark. In this case, we cannot do this kind of optimization. But internally, this is all implemented with template meta programming, so it will go into a different templatized method. So in this case, this will be executed sequentially, in a sense.
Okay.
Yeah.
I think we should press on with the next talk, so let's thank Matthias and let's